Okay, we're ready for the independent sample t-test. If we have a new data set, it's composed of two variables, and this data set is comes from Harry Potter theme. We have a variable called cloak and a variable called mischief. If we go to the variable view, we see that the values, the coding for cloak is we have 0 equals no cloak and 1 equals cloak. So this refers to invisibility cloak in Harry Potter. So whether a person is invisible or not. And then, and that is a nominal variable. So cloak and no cloak categorical. Mischief is the sort of the account of mischievous acts. So you might make a hypothesis that a person would be more apt to commit mischievous acts if they're wearing the cloak. But that's what we're going to test. So that's our data set. 24 observations, and our first step is to assess the assumption of normality and take a look at our data. So we're going to run the Explore analysis again. So we're going to go to Analyze, Descriptive Statistics, and Explore. Okay. Last time we just had one variable, so we put that in the dependent variable box. This time we have two, so we are going to put our dependent variable still in the dependent box, and that's our mischievous acts. Mischievous acts supposedly depend upon whether a person's wearing a cloak or not. Okay, so cloak is going to go into the factor list or the independent variable box. Factor is another term for independent variable. Okay. We're going to go back to plots, and we're going to request the same histogram and normality plots with tests. Continue and run it by saying okay. Okay, so in the output, we have our case processing summary table. And here we have, again, 0 missing cases. We have 12 cases in the no cloak condition and 12 cases in the cloak condition. So it just gives us an idea of our sample size. Well, if we go down to the descriptives box, we have the same measures of central tendency and variation that we saw with the one sample t-test. Only now these are provided for each level of the independent variable. So the no cloak condition has a mean of 3.75 mischievous acts. The standard deviation of 1.91. In the cloak condition, there the mean is 5 mischievous acts. So it's a little bit higher than the no cloak condition with standard deviation of 1.65. Okay. If we take a look at the skew and kurtosis statistics, the skew for the no cloak condition is not. We're looking for a ratio of 3 to 1 or more for the statistic for the standard error, and here it's closer to 1 to 1. And here the kurtosis for the no cloak condition is less than 1. So this divided by that is a fraction, and so no problem there. In the cloak condition, we have a skew of 0, so there's nothing to divide by. There's no skew. There's a positive or negative skew, and the kurtosis is also less than the standard error. So no issues there. We should see a normal distribution. If we go to the formal test, the Kolmogorov-Smirnov test, that looks at whether there's a significant departure from normality. We again see that both the p-value for both conditions is above 0.5, so not significant. Neither one of these is significant, indicating that both distributions are equal to a normal distribution, approximately. We go to the histograms, we get a funny looking distribution for the no cloak condition. It looks negatively skewed. We have a bunching of cases at the top end of the scale. And just one observation from 0 to 3, SPSS. So it looks negatively skewed, but the Kolmogorov-Smirnov test is saying there's not enough departure there to be a problem. And in the cloak condition, this looks like a normal distribution, so we don't necessarily even need to test for that. If we look through some of the other data, the box plot, we can see just like the means indicated above, we can see that the cloak condition tends to have more mischievous acts. It tends to have a little bit more than the no cloak condition, although there is overlap. So there's a good deal of overlap between these two lines. We have a significant number of cases in both conditions. So we really need that independent sample t-test to determine if there's a significant difference between these two groups on the dependent variable. So let's run that. To do that, we're going to go back to where we find our t-test. So analyze, compare means and proportions, and then independent samples t-test. Okay. So analyze, compare means, independent samples t-test. And here we're going to get a test variable box. This is where we're going to put our dependent variable. So mischievous acts is going to go to the test variable. And then for the grouping variable, we're going to move cloak there. And it gives us this wonky cloak with 2 question marks. That is asking you to define what the 2 groups are that you want to compare. How are they coded? Okay, so a variable like race and ethnicity, for example, might have 5, 6, 7 different categories. If you run an independent sample t-test, you're comparing 2 groups at a time. So it's asking you, okay, which 2 groups do you want to compare? In our situation, we only have 2 groups, but we need to tell the analysis how they're coded. And they are coded as not 1 and 2, but 0 and 1. Okay. So I'm going to change these to 0 and 1. And I'm going to say continue then, and I've defined that grouping variable, the independent variable. And that's all I need to do for specifications here. So I can run this by saying okay. Now I get the independent sample t-test output. Here in the first table, I get some summary data for each group. So I can see I have 12 cases in each condition, no cloak and cloak. I get the means that we saw earlier, 3.75 versus 5, and standard deviations and standard error. The significance test is in the second table, okay? And this is also where we're gonna look at the second assumption, or the a second assumption of the independent sample t-test, which is the assumption of homoscedasticity, or the assumption of equal variances between groups. Okay? So the t-test assumes that the variance for group 1 is going to be the same for the variance for group 2. To examine that, there's a test called Levine's test for equality of variances, and that's given to us as a significance test. It's an F test with a p-value. Okay, so we're going to go right here and evaluate this. If this p-value or significance value is significant, that indicates that the variances are significantly different from each other. If it's not significant, which is the case here, the p-value is above 0.05, it's 0.468. And that indicates that the variances are not significantly different from each other. In fact, they are statistically equal to each other. Okay? So what that does is helps us determine which of these two lines to interpret. We have two rows of statistics. The first row is equal variance is assumed. The second row is equal variance is not assumed. Okay, so if we violate the assumption of homoscedasticity in a t-test, usually it's not that consequential. The t-test is pretty robust to violations of that assumption. But there is a correction, sort of a penalty that's added if the variances are not equal. So if that's the case, we're going to interpret this second line. Okay. But it's not. We have equal variances. We're going to read the first line. So then we go to our t-test statistics. So t value is negative 1.713, and that's the case no matter what. We have 22 degrees of freedom. If the variances were not equal, that number is a little bit less, and that's where the correction comes in. Okay, so it makes it, if there's fewer degrees of freedom, it makes it a little bit harder to obtain statistical significance. But like I said, we have 22 degrees of freedom for this test, and in our case, we have a we're just starting with the two-sided p-value or two-tailed alpha test. In this significance value is 0.101. Okay, and that's above our criterion of p less than 0.05. So we are going to say, well, the means of these two variables are not significantly different from each other in this case. Okay. I mean, there's a difference there, but we don't have enough. In this case, my guess is we don't have enough data for that the two means to sort of emerge as significantly different. So that's our conclusion for this test. If this t-test were significant, then we would go and interpret the Cohen's d value. And that value is it's listed as a negative 0.7. And for Cohen's d, you can just look at the absolute value. It's a negative because we subtracted the lower number from the higher number. So it's a negative number in the numerator, making Cohen's d negative. But we just look at the absolute values. 0.7 is the effect size. And that's close to a large effect size. So that supports my thought that if we had more data, perhaps the significance test would be significant because that's a fairly large effect size. But when you have small sample size, it's hard to obtain significance. So that is that for independent sample t-test.